Now, in order for the tangent plane at this point, x naught, y naught, z naught, to act as a reasonable approximation for fx, y, the surface must be continuous and differentiable at that point. In two space, if we had a function that looked something like this, that's x and y. Sorry, it's pretty ugly. But if I had a function that looked like this, oops, that should be open. Trying to estimate this function at this point doesn't make any sense. I've got this huge jump there. Right? What I need is something that's continuous. I need it continuous and differentiable at that point. Otherwise, I can't begin to find the tangent plane. Well, I must have the same sort of condition exist in 3 space. So let's consider this function, f of xy equals xy over x squared plus y squared. And I want to take a look at a tangent line approximation near the point 0, 0. For right away, I think you can see there's probably going to be some issues at 0, 0, because as soon as I put 0, 0 in there, I get 0 over 0. It's this indeterminate form. So I need to take a look at trying to determine differentiability to begin with. So I'm going to approach, the first thing I'm going to do is take a look at this. I'm going to approach the point 0, 0 along the x-axis. That means, axes, there we go. That means that obviously y is equal to 0. And for that, f of xy is also equal to 0. So obviously the partial is equal to 0. So the second thing I'm going to do is, again, I'm going to approach the same point. Along the y-axis. That, of course, means that x is equal to 0. And again, I get the same thing. The partial with respect to y is also 0. Based on this, if I were to now go ahead and do a linear approximation, this tangent plane approximation, it would be 0. Because what we'd have is z equals the partial with respect to x minus x naught, plus the partial with respect to y minus y naught, plus z naught. And z naught, it looks like, is going to be 0. And these are all 0. So what it looks like is that z is simply approximately 0. That's my approximation, which sounds pretty reasonable. However, looking at this function again, I'm going to approach this time along the line y equals x. Now when I do that, f of xy equals x squared over, x squared plus x squared, which is x squared plus, there we go, x squared plus 2x squared, which is obviously equals to a half. Therefore, f of xy is equal to a half everywhere along the line y equals x. But we said that it was approximately 0. Because of this, we can say that f of xy is discontinuous at 0, 0. Well, if it's discontinuous, the whole idea of this tangent plane approximation just went out the window. We need a function that's well behaved at 0, 0. In this example, 0, 0. We need a function that is well behaved at this point that we're going to make reference to, or that we're going to work off of. In this case, it is not well behaved, so like I said, the tangent line approximation near that point would not be appropriate. If you look back at that last example we just did, That's, well, it's a polynomial, so it's continuous everywhere, so we don't have this issue. A sufficient condition to show the function is well behaved near this point is simply if the partial derivatives of f of x and f of y, the partial derivatives with respect to x with respect to y, exist near the point AB and they are continuous at AB. If we can show that's true, then the function f is differentiable at AB. If we take a look again at f of xy equals 3 times x minus 1 squared plus 2 times y plus 3 squared plus 107, the partial with respect to x was simply, see, 2, whoops, six times x minus 1, which is continuous everywhere, it's just a polynomial. The partial with respect to y is 4 times y plus 3, which again is just a polynomial. These are continuous everywhere, so near the point, or it doesn't matter which point, but obviously near the point that we were looking at earlier, then this is going to be differentiable. So the idea of a tangent line approximation makes sense here.